Hello everyone, welcome to Computer Science 318. This will be lecture number 19, I think. And today we'll be talking about what? We'll be talking about breadth first search and depth first search. Those are very, very important fundamental concepts in computer science. So let me maybe briefly explain you how they work. And then we'll dive into the code. Okay, so let's say you have something like this. That is the graph or the tree, whatever you want to call it. So it looks like a binary tree, right? So that's the root, and it has two nodes, two children. Okay, at most two children. However, you can also see that that is not a binary search tree, right? Because we don't have a situation when, for example, like we have 1 and everything on the left from 1 is less than 1. Everything on the right from 1 is greater than 1. That's not true. Okay, so let's call it just a tree. Okay, let's call it binary tree. Okay, now in a situation like that, for example, if I want to search for an element, let's say 6, it's not as easy as it would be if it was a binary search tree. Why? Because, for example, if I'm thinking about 1, and if I'm looking for 6, I don't really know if 6 will be located on the left or on the right, because it's not a binary search tree. If it was a binary search tree, then it will be clear that 6 is on the right, but we don't have that guarantee. In this case, what do we have to do? We have to visit each node in the graph, each vertex. And there are two basic approaches, two most popular fundamental approaches in computer science so you can do that. And those are depth first search and breadth first search. Okay, so what would be the depth first search? Depth first search is when you start with any vertex. Well, technically, so it can be 8, 9, 10, 11, any of them. But let's say, again, for the simplicity, we'll start with 1. And then what we want to do, we want to visit each node, go into the depth first. So that's why it's called the depth first. So I'll basically go like over here versus instead of going from 1 to 2, 3, 4, 5, 6, 7. Basically, instead of visiting the tree level by level, like horizontally, I'll just go vertically. I just go down first and then climb back up, if that makes sense. So basically here I would do, I would visit 1 first, then 2, 4, 8, then we'll be back 9, then 5, 10, 11, okay, then coming back, then will be 3, 6, 13, then 7, then 14. So approximately I think that's what it will be. Okay, so that's the order. Okay. So again, we'll go to the depth and then climb back up a little bit. So it's kind of similar to what would that be? Pre-order traversal, I guess. Kind of similar to that. Anyway, so that'll be depth first. So depth first. Now another approach is breadth first search. So breadth is when you go to the breadth, right, like breadth stroke. So basically visiting the tree level by level, you visit 1 first, then 2, 3, then 4, 5, 6, 7, then 8, 9, 10, 11, 13, 14. That's what you would do. So like when you're doing the breadth first, you visit 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14. Yeah, okay. Hope it makes sense. Cool. Okay, so now let's jump into the algorithms. Let's discuss the algorithms, how it's done. The first one we'll be talking about it will be depth first search. Okay, so now please pay attention to what I'll be talking about, because that's kind of important. Okay, so I already typed up, but I highly recommend you guys do that. Pause the video and type it up as well. So because I'll be asking that on the quiz. Depth first search, okay, implements a depth first traversal of a graph. The input would be graph G, which is a pair of two sets, V and E. Okay, so output will be graph G with its vertices marked with consecutive integers in order they are encountered by the depth first search. Okay, so the output would be basically the same graph, with maybe it's like, so for example, this will be printed out first, right? So here, so here we have 1, here we'll have 2, right? Sorry, not 22, but 2. Okay. So here we have 2, here we have 3, here we have 4, right? Basically, something like that. So in a depth first search, okay. Okay, cool. So that's the comment, and now we come to the code. We need to mark each vertex in V, in the set V, right, with 0 as a mark of being unvisited. So basically what we're doing is this. We'll mark each one of them with a 0. Okay. So I cannot copy that. Okay. So anyway, we'll mark each one of them with 0. Okay. And we do that for the entire graph. I'll not be marking each one of them for the sake of time. But we're marking each one of them for 0. 0 means that it has not been visited, right? So, like, yeah, it's not visited. Now, next. We set counter to 0, count is equal to 0. Now, for each vertex v, lowercase v, so for each one of those nodes, if that node is marked with 0, and in the beginning all of them are, then we run another function, dfs, lowercase dfs v, okay, dfs on v. Okay, cool. So basically for each one of them, if they have not been visited yet, for each one of them, what do? We just run a separate function. Okay. Now, what does a separate function do? So dfs v, right? It visits recursively all unvisited vertices connected to v. Okay. So connected to v, but by a path, and numbers them in order then counted in the global variable counter. Okay. Okay. So what happens here is that when we call dfs of v, count is incremented, count is equal to 1. Now, mark v with count. Okay, so for example, if we call this, we call dfs on 1, so count is being incremented to 1, so mark it with 1. Okay, perfect. Now, for each vertex w in v, okay, adjacent to v, so in other words, for each vertex adjacent, for each node connected to v, so in our case, there will be for each vertex connected to 1, which will be 2 and 3, right? So for each one of them, what do we do? If w is marked with 0, okay, and in our case again, all of them are marked with zeros, dfs w. Okay, so basically recursively call the same thing, but not on v, but on w. So in other words, at the beginning again, we call it on 1. Okay, then for each vertex connected to 1, which are 2 and 3, we call dfs. So what do we do in dfs? We first increment the counter and then mark that with counter. Okay, so basically increment the counter to 2 and we'll mark this guy to be 2. Okay, then yeah, then instead of going over here before getting to 3, what do? So mark it with this 2. Then we call the same function for each of one of the vertices connected to 2, right? Which is 4 and 5. Okay, so that becomes 3. Then for 4, we run dfs for each vertex connected to 8 and 9. So that becomes 4. Okay. Then for each vertex connected to 8, which is nothing, we run dfs of nothing. Okay, so it comes back over here. Then we run it, so we are in this for loop currently, for each vertex connected to 4, right? So what's another vertex connected to 4? That's 9, okay? So we run it on 9, increment the counter, it becomes 5, okay? So then we don't have anything to run it on, then come over here, and then basically the whole thing continues. So it becomes 7, 8, okay, and so on. And that's how you basically mark each one of them. Okay, then you basically finish up with this branch, then you go to this subtree and you do exactly the same thing. So that's how a depth first search or depth first traversal or depth first like approach works in general. Okay. Yeah. Now let's maybe I'll attach some tutorials which will go over that in a bit more detail. But I don't know, so let's see, because I don't want to go into that detail here. Depth first traversal. depth first traversal. Okay.
Hello friends, in this video, the solution to this could be push it into our stack, top of the stack.
Yeah, you could probably watch this video later. This one's just talking about the graphs, but in the meantime, I'll continue. Okay, so what is the time efficiency? Efficiency. What is the time efficiency of our depth first search? Okay, how efficient that is. What is that time efficiency? Okay. Graphs. Okay, so it really depends on how V and E are structured. Okay, so if we have, like we can say for adjacency, for adjacency matrix representation. Okay, so if all the vertices are represented as an adjacency matrix, what do we do? Then it will be big theta or big O V squared. Okay. Okay. Hold on. Oh, okay. I'll make it the caret. Okay, so it'll be big O V squared, which means that it will be the number of vertices squared. That's how efficient it will be. So that's one. Okay, if we're talking about for adjacency list, okay, then we'll be doing big O of V plus E. Okay, yeah. So they'll be a bit more efficient. Okay, so again, where this number, so modulo V, represents how many vertices you have, how many nodes you have, how many elements of the V set you have, and here the modulo E represents how many nodes, how many items you have in the set of edges. Okay, for adjacency matrix representation, yeah, that's the idea. Okay. Cool, yeah, because again, so if you have adjacency matrix, what does that mean? That means you have a matrix like of n by n, and you have to visit each one of them, so that makes it like V squared. If you have adjacency list, then you need to visit each vertex and each edge, so it makes it basically like 2V or 2E. That's a bit more convenient. Okay, so for example, again, if I do matrix, adjacency matrix. Okay. Let's say that's the graph, that's the adjacency matrix. Okay. So in this case, in order to traverse each edge, I basically have to visit each one of those cells. How many of those cells I have? I have them n by n, right? So basically, if I have V, what is it? Modulo V, right? So I have that many vertices. Okay, so number of columns and rows is that many, so basically it's this times this, which is modulo P squared. If I'm talking about adjacency list, okay, then it will be something like this. Okay, so I have all the vertices here and all other vertices they're connected to. So in this case, I have to visit each one of them, and then for each one of them, I would also have to visit all the edges. So in this case, it becomes V plus E. Okay, so that's depth first. Depth first search. Okay. Now, one of the most important things is when that is pseudocode, right? So that is a very high level code. Okay, very high level. So if you're thinking, okay, so how would I actually create it? How would I actually implement it in Java? If you want to. If you're thinking okay, so that's high-level code only, right? So how would I actually implement it in Java? What you would have to create, what you have to do, you would have to create a stack. Okay, so use stack. So what do you use a stack for? You would use stack to store all the vertices you're visiting. Okay, so use a stack. Where's that? Okay, so basically, imagine you have a stack like this. Okay, imagine you have a stack. At the very beginning, you have the stack is empty. Then you visit the first node. Okay, so you visit the first node. After that, you what do? You add to the stack these two, the nodes you connected to, okay, which are 2 and 3. Okay, so let's call 2, 3. Okay, 2 and 3. And then you visit each node that 2 is connected, so you visit in 4, 5. Okay, so you visit in 4, 5. And then you visit in, for example, the one which 4 is connected to, so it's 8, 9. 8, 9. Okay, and after you realize that there is nothing which is visited by 8. Okay, so what do? You pop this 8 out of the stack. So you pop it out. Okay, perfect. Then you do the same thing for the 9. You visit each node for 9 is connected to. It's not there, you see. Okay, so you pop it out. Then you do it for 4, like 4 is not connected to anything. Okay, then you do it for 5. Okay, so after which you visit 10 and 11. Okay, so you push them on the stack. So you visit 10, print it out, then you see there is nothing below 10. Then you visit 11, print it out, and when you visit 10, when you realize that there is nothing below 10, you pop it out, and then you visit 11. There is nothing below them. You print it out 11, then you pop it out. Then you see that you're done with 5. You pop that out. You're done with 2. You pop that out. Then you go to 3. Okay, so you print out 3. Then what's below 3? 6 and 7. 6 and 7. Okay, so you print out 6. Then you visit the one which 6 is connected to, which is only 13. Okay, then when you print out everything which 13 is connected to, so there is nothing there. That's why you pop out 13. Then you pop out 6. Okay, then you have 7. Okay, you print that out. And then you add what's below 7, 14 to it. Okay, and then when you realize that you're done with 14, you pop that out. You're done with 7, 3, 1, and then the stack is empty. So that's how you do depth first search. When it comes to breadth first search, the code is very similar. The only I would say the only difference is that instead of a stack, you're using a queue. Okay, for the breadth first search, there is actually no algorithm in the book, so that's why I found this algorithm for the from the Geeks for Geeks site. Okay, and I think they also explain how it's done. I recommend reading that, but I think maybe that will be a bit easier if you just take a look at the code. Okay, so again, it is a very similar technique, except for the fact that you are not adding to the stack. Okay, you add into the queue when you're talking about breadth first search. Okay, so here's an idea. So breadth first search, that's the Java code. Okay, the constructor, we have a graph. Okay, edge, done. Now breadth first search. Okay, S. So we start with any node S. Okay, we mark all the vertices as not visited. Same thing, right? So they mark with falses. Okay, into separate array. We can mark them with zeros if you want to. Now we create a linked list queue. Okay, so instead of a stack, we're creating a queue. So mark the current node as visited. Okay, so mark this node as visited. Visited of S is equal to true. Okay, and then we do queue add S. So we add this. We mark that as visited. Then we add S to the queue, to this one. Okay, and then we do like while loop or for loop. Okay, so as of now we didn't do anything special. We did exactly the same thing, and now this while loop is very similar to this for loop. Okay. No, not the one. Okay, this one. Okay, now so while queue size is not equal to 0, S is equal to queue.poll. So poll, if you remember from 227, it removes an element from the queue. Okay, so dequeues, for some reason in Java it's called poll. Then we print it out. We print out S. We print out the one we just dequeued. Okay, and then for using the iterator, okay, for each one of the vertices connected to S, adjacent to S, okay, what do? While they exist, we immediately mark them as visited, and we add them to the queue. Okay, so let me try to explain here. Okay, so we'll kind of remove that. Okay, so copy this image, copy it over here. Okay, so let's imagine again we have this tree graph, and we want to start with 1. Okay, and we have a queue. So let's imagine that this is our queue. Okay, and so that's the queue. Sorry. Okay, so that's the queue, and that's the printout. Terminal. Okay. That's the queue, that's the printout. Okay. So, in a queue, again, we start with, we mark them at zeros first. Okay, then we start with 1. What do we do to 1? We add it to the queue. Okay. We add it to the queue, so we add 0 to queue. Perfect. Okay. Sorry, no, not 0. 1, 1, 1, 1, 1. No, not 0, 1. Okay. So we added 1 to the queue. Okay. Perfect. We visited as we marked that as visited. Awesome. Moving on. Then what do? We dequeue S and we print that out. Okay. So we dequeue our the node which we visited. So we dequeue that. We dequeue it as 1. Okay. And print that out. So basically remove it. Okay, so as of now we have nothing in the queue. Okay, we'll print it at 1, and let's see what happens next. Okay, now for so basically in the iterator we add all the elements, all the vertices connected to our S. Okay, so now while there are some elements which are connected to the element. Gosh, sorry. While there are some elements connected to our element, which we just dequeued 1, okay, so which is 2, 3, okay, or then when we dequeue 2, it will be 4, 5. When we dequeue 4, it will be 8, 9. Okay, so now in our case, at this particular moment, while there are some elements which are connected to 1, okay, what do? If that element, for example 2, is not visited, and 2 is not visited yet, what do? We mark that as visited and we add it to the queue. Okay, so we mark that as visited and we add it to the queue, which means we add in 2 and 3 here. Okay, so we mark them as visited and add it to the queue. What happens next is, okay, so we're down here, okay, then we'll come back over here. While the queue.size is not equal to 0, at this point, well, queue.size is not equal to 0, we have 2 and 3, okay, so what do? We remove the one which is there, which is, yeah, so we'll poll it, okay, so let's say, again, we're removing from the right, so we'll poll, queue. Okay, so if we add 2, 3, in this case, the 2 should be at the end, which means we need to remove 2 first. Okay, so let's say we'll be adding from the right. Okay, we'll be adding from the right of the queue and removing from the left from the queue. So 2, and then okay, and 2 and 3. Yeah, no, hold on. Yeah, so we're printing out 2, okay, and then what do? Yeah, so we dequeue 2, okay. Yeah, so we dequeue 2, we printed 2 out. We need to dequeue that. Okay, so we dequeue 2, we printed that out, and then okay, and then we add. Then we consider all the nodes 2 is connected to, which is what? which is in our case is 4 and 5, okay, and we add them to, we mark them as visited and add them to the queue. So mark them as visited and add them to the queue. 4, 5. Okay, perfect. Now, what happens next after that moment? What do we do? So we did that, come back over here, while queue size is not equal to 0. Is that equal to 0? No, we have 3 elements there. Perfect, okay. So moving on, we need to dequeue 3, okay. We print in 3 out. Okay, perfect. Print that out. And we need to add all the elements 3 is connected to, which is what? 6 and 7. Add them to the queue. Okay. Now come back over here. Okay, we added them, right? So coming back to the while loop, is size equal to 0? No, it's not equal to 0, so we continue. Okay. So what do we do here? We dequeue 4. We print that out. 4, okay. We print out 4, and then we add all the elements 8 and 9. Four is connected to. Okay, so yeah, as you can see, that's how it goes. So as of now, we already have 1, 2, 3. Then after that, what we'll do? Yeah, so the size is equal to 0. No, then we need to pull 5. Print out 5. Okay. Then we need to consider all the elements 5 is connected to, which is 10 and 11. We add them to the queue. Okay, we add them to the queue. Yeah. So then we're coming back again to the while loop. Is size equal to 0? No, it's not equal to 0. That's why. Okay, what do? We dequeue, so we remove 6. We print out 6. Okay, in the terminal, and then we connect. Then we in queue everything which 6 is connected to, which is in our case is 13. Okay, perfect. Yeah, only 13. Then again we come back to the while loop. Is this queue empty? No, it's not empty. So we dequeue 7. Okay, then we print out that 7. And in this case, at that point, I'd like to stop here. Again, in order to save some time. So in this case, what do we have? We already printed out 1, 2, 3, 4, 5, 6, 7. So as you can see, we traverse that like level by level, and that's how we already got what breadth first traversal. Okay, and basically, if you keep doing that, at some point you will just print out 8, 9, 10, 11, 13, and then 14, and that will be like you'll be finished. That will be the BFS. That will breadth first traversal. Okay. So that's why, again, when we're talking about BFS, we're using queue. When we're talking about DFS, we're using a stack. Okay. Now let's use a stack. Okay. Yeah. For BFS, we use a queue. Okay. And I would like to describe that a little bit. Okay. So how it works? It proceeds in a concretic manner by visiting first all vertices that are adjacent to starting vertex, then all unvisited vertices 2 edges apart. 2 edges apart from it, and so on. Until all the vertices in the same connected graph or connected component of a graph are visited. Okay. And that's very important, by the way. That's very important. So imagine again, imagine if you have a situation like this. So that is a graph, right? That's not necessarily a tree, but you can also say it is a graph. And imagine that you have, that the graph is not connected. Imagine that you have like a couple of more vertices, like over here. And let's say they're not connected to that. And let's say they're not connected to this component of the graph. So they're basically disconnected. There is no connection between these guys over here and these guys over here. So in this case, what do? That's a good question. So that actually our algorithm for depth first search and breadth first search, they both do it correctly. They'll be able to take care of that. How? For example, for depth first search, okay, take a look at this algorithm. For each vertex v in V, so for each vertex in capital V in the set V, okay, so we do the DFS. What that DFS does, it basically traverses all the vertices, okay, which are connected to each other. So that DFS will traverse all of these vertices, okay, and if it will mark them as with some numbers. And if, let's say, that happens that there is some portion of the graph which is not connected, okay, then in this for loop, since you are talking about since you're talking about visiting each node in the set V, you will definitely at some point you will reach to the point when you will visit these vertices as well. I hope I explained that correctly. Okay, yeah. Same thing for the breadth first search. Okay, so yes, within one while loop, you'll be able to print out. You'll be able to traverse the whole tree, all the nodes which are connected to each other, but then no, that's actually for the connected portion. Okay, no, that's only for the connected portion. This graph. Do we have? No. Okay, so that traverses basically the connected portion only. Okay, but if we do this BFS, not for two, right? But if we actually do BFS for all of the nodes in the set V, in this case, we'll definitely traverse all the portion, or the entire graph. So in other words, we'll traverse the whole thing for one, right? We'll visit all the nodes, and then we'll visit like one of these three, and then we'll traverse. We'll print out this entire portion of the graph, which is not connected to this portion. Hope it makes sense. Okay, cool. So what is the time efficiency, right? How about breadth first search? Okay, so time-wise, time efficiency is exactly the same. Okay, so time efficiency is exactly the same. Okay, so it's big O of V squared for adjacency matrix and big O of V plus E for adjacency. Okay, okay, yeah, cool, super important. Okay, so that's why again, out of those, out of these two algorithms, they have exactly the same efficiency. So it's completely up to you which you want to choose. Doesn't make any difference. Okay, yeah. The only thing, I guess, the only thing to remember is this. Definitely remember that depth first search we use a stack, and for breadth first search we use a queue. Okay, cool. That's it for today. I hope you guys enjoyed the class. I'll see you later. Bye bye.